Greetings from Dynotis. Today we're going to talk about our dynamic balancer module, and we're going to do a demonstration on our 3-blade propeller configuration. As you can see, we have our Dynotis test stand, and we have a motor propeller configuration with a 3-blade propeller where we have purposefully created an imbalance for the demonstration. Then we have our test weights and correction weights as electrical tape. More on that later. First, we're going to activate the device from the Device tab. Then, we are going to switch to the Dynamic Balancer tab and we're going to set the test configurations by writing the name of the test and then clarifying the name of the motor, the propeller, the diameter, and the desired ISO quality grade. Following that, we're going to set the test parameters and choose between a 2-blade or 3-blade configuration, then hit Start. Once you set the test parameters, you can follow the guidelines. Make sure that you place Dynotis on a flat surface and that the propeller area is safe, and then choose an RPM for the reference measurement. You can do this by finding the test RPM in the PWM signal before going further with the test. Here, in our test demonstration, we're going to choose 2,500 revolutions per minute, which corresponds to 1181 microseconds in PWM signal. Following that step, make sure the motor is not running for the ambient noise measurement. This noise measurement is crucial for us to tear the system and follow along. Then we are going to measure the propeller's natural imbalance. Now, we created a purposefully imbalanced system by adding electrical tape, but if you do not know where the imbalance is, this step is crucial to create a baseline. Once we hit our desired RPM, we start the measurement and then we get our natural propeller vibration level to create a baseline. Then we're going to find the first blade. Now, in this test, we chose the blade right next to the imbalance in a clockwise direction, so that will be our blade 1. But you can choose whatever blade you want, as long as you follow the numbers in a clockwise direction. We apply a test weight of 0.270 grams, which corresponds to 10 centimeters of electrical tape. Then we record the test weight and the distance at which we apply the test weight on the propeller, which is 11 centimeters from the center for our test. Once that is completed, we're going to increase the RPM to our desired level, and once the RPM is stabilized, we're going to start the measurement with our first test weight. Then we remove the weight from the first blade and apply it to the second blade, which is to the right of the first blade in a clockwise direction. So we apply the same weight, which is 0.270 grams, corresponding to 10 centimeters of electrical tape, at 11 centimeters away from the center of the propeller. Then we initiate our second blade test, where we're going to hit the desired RPM as well, make sure it's stabilized, and then start the measurement to capture the peak vibration as well as the ISO quality grade. Continuing clockwise, we remove the weight from the second blade and apply it to the third blade at the same distance, 11 centimeters from the center. Once we are sure that we have applied the test weight, we are going to go back to our software, hit the desired RPM, and then start the third blade test trial. Once we're done with the third blade trial, the system calculates the recommended correction weights, and this usually falls along two blades, in this case on blade 1 and blade 2. In the system we see that it is recommended for the first blade 0.41 grams and for the second blade 0.332 grams. Corresponding to our unit weight, that is 15.2 centimeters and 12.3 centimeters of electric tape correspondingly. We take our test weights and suggested weights, and we use our unit weight calculation to find the length of the recommended correction weights. We remove our original test weight, and then we apply our correction weights to blade 1 and blade 2. Once we're done applying the test weights and the correction weights, we are going to hit our desired RPM again for the final time and then capture the peak vibration and the ISO levels. This is important for us to see whether our correction weights helped balance the system further. As our demonstration shows, our natural measurement ISO was 7.721, while our balanced propeller ISO was 5.082. This shows that the system worked. See you later.